Day one of PVA, we focused on specific points. Today, day two, we're going to look at over an interval. Here we go. We have same concepts though. Particle moves along the x-axis. Here's our interval between 0 and 18. The inflection points, like always, are in green. Find all intervals of time when the particle is moving to the right. Well, when is it moving to the right? Moving, that's a derivative. We want to know when the x values are moving to the right. That is the positive direction. All right, well, that's the slopes. And that's the velocity. So we want to know where is the velocity positive. Well, the velocity of this graph are the slopes of the tangent lines because we are looking at the x graph, right? This is the position function. And we want to know the movement. So we have, well, let's see, we want to, these are negative slopes now. This is a zero slope. Here we have positive slopes. So it looks like we're going from, here's positive slopes. This is a 0 right here at 4. So it looks like between 4 and 7, those we have increasing slopes. And, well, then it's going downhill again. Those are negative. Then right here at 11, we have, let me see, so from 11, it goes up. Now, even though that's a 0 slope right there, it doesn't go negative. So it continues up, and I'm going to say that it is going to continue up to t equals 11. I'm sorry, 18. So we have two intervals. So what you would do is you would hit add, and you would do two of them. First, you have a 4, sorry, that's really sloppy, 4, 7. And then in the other one, you would type in 11, 18, submit, and you would be correct. Now, this question could have easily asked you for the left. So just to point it out, the left would be where your derivative is negative. So what you would be doing is looking for the blue regions where you're sloping downhill instead. And just to tie this into yesterday we would have just asked you something like, say, what about at t equals 9? At t equals 9, is it moving left or right? Well, then you would say, oh, it's going down. So then it would be moving left at that one particular point. Today we're just looking across intervals. Next example. We have a particle moving along the x-axis, and its position between are similar, blah, blah, blah. The inflection points, we know where they are, marked in green circles. Find all intervals when the particle has a negative acceleration. Well, what does negative acceleration mean? Well, the a of t is the same thing as x double prime of t, just to point it out. And, well, if it's negative, we want negative values. Let's see what graph we're looking at. We have the x of t graph. All right, well, the x of t graph means, well, what's the second derivative of x of t? That is the curvature. All right, well, the points of inflection are going to be important on this example. Let's see what we got. So this right here, this is curving upward, and that is concave up. That's where the second derivative, which is your acceleration function, is positive, right? And then over here, there's a point of inflection. You can see it's curving downward, all right? That is where your a of t is negative. And then here again, you have curving upward. Well, that's where your second derivative is positive. Oops, yeah, and then green, let me see. Green is the negative, so that's curving downward. Those are regions where this is negative. And then back to blue. Oh, I did light blue. Now I'll do dark blue again. This right here is where your a of t's are positive. They have positive values. What was the question asking? Find all intervals when the particle has a negative acceleration. Okay, well, I mean, we might not have had to get so in-depth with the concavity, but we did. Well, we want to know where it's negative, so we're looking for negative curvature. Well, that would be the green region. So we have an interval here, and we have an interval here. So it looks like the first interval is going from 5 to 7. That is negative acceleration. And we also have an interval between 9 and 11. And you wouldn't write it like this. You would hit the add button and then type in 9, 11 as a second answer, and then click submit, and you would be correct. In this next example, you're going to notice that rather than the position function, we are given the velocity function. Okay, note that we have the velocity. So that tells us different things about the original function. On the interval between 0 and 18, you know where the inflection points are. We want to find all intervals of time when the particle is moving to the right. Okay, so moving to the right, well, we talked about that. That is when the x position is moving, that's the derivative, and it's moving positive. The right is the positive direction. Well, the derivative is the velocity function, and we want to know when is the velocity positive. Since we are looking at the velocity graph, we want to know where the velocity is positive, not negative. So we are looking where the graph is in this region. Well, if you focus on these two, there's only two small intervals. And they are, well, let me do this one first, I guess. This interval right here, so that's going from 0, it's open because it's, and that's to 1. The other interval over here, well, that one looks like it's going from time 17 to time 18. That's where it's positive. Those are your two answers. Let's see what we do if we're not given a graph, but rather just the function. So the particle, we're given the velocity. You've got to be mindful of what they're giving you and what they're asking you. What are the intervals when the particle is moving to the right? Well, the concepts never change. The moving to the right, well, the movement, the x value is moving, that's the derivative. So we want to know to the right, that's positive. That is the velocity. We want to know when the velocity is positive. They give us the velocity function, so you don't need to take the derivative, right? What you need to do is, let's do a number line. Let's do a velocity number line. That means we're plugging in the values into the velocity graph to see the values of the velocity, and if it's moving to the right, we're just looking for where they are positive values, and things change from positive to negative when it equals 0. So let's figure out, when does this velocity function, v of t, equal 0? Well, I should do this. 3t squared minus 42t plus 72. I'm going to take out the 3 and make our numbers a little bit smaller, and that's going to be, that comes out to be 14. And 72 divided by 3, that is 24. Just to make our number smaller, because now you might see, well, here, let's divide by 3, and when you divide, the 0 divided by 3 is 0. So let's continue. Now we're going to set this, well, it's equal to 0, and now we can factor it nicely since we took the 3 out. Well, we could have done it with the 3 also, but it's easier now. That's a t, and that's a t, and let's see, we want 24, so we probably want a, let me make that a negative. We want both negatives. We want a negative 12 and a negative 2, because that's going to give you negative 14 and a positive 24. So now you set these both equal to 0, and you're going to get yourself a t equals 12 and a t equals 2. All right, well, let's test both of those. Here's what we're going to do. We're going to put on our number line. Let's go back up here. We have a 2 and we have a 12. Since we have 2 of those, it breaks it up into 3 intervals. Let's take an interval, a test point in each interval. We could do a v equals 1. We could do a v equals 3. It doesn't really matter. And how about a v equals 13? Let's evaluate these test points now in the velocity function, the v of t, just to see what it was here, 3t squared minus 42t plus 72, just to keep it above what we're doing here. So we have to test v of 1 and v of 3 and v of 13. Well, when you plug them in, you're going to get, that's a 1, so that's 3 times 1, minus, well, that's a 42 times 1, and that's plus 72. So let's see what we get here. That's positive. This is 70. This is going to be a positive number. I don't care what it is. I just really need to know, is it positive or not? But obviously, if you plug it into your calculator, you're going to get yourself a positive number. Now, when you plug in a 3 in here, you're going to plug it in here and here, and what that's going to do is that's going to generate a negative number. And when you plug in a 13, that generates a positive value. So let's see what we have here. Oops, I forgot. We don't go on forever. We're going to, here's our time. That is 0. Okay, so we're going to stop at 0. So in that interval between 0 and 2, we generated a positive value. In between this value, 2 and 12, we generated negative velocity values. And in this interval, 12 to, well, infinity, we generated positive velocity values. We're looking for positive velocity values. There's our interval. The first one is between 0 and 2. And, well, another way of writing it is you're uniting both of these. So that answer and this answer are both correct. Let's check out this next problem. Okay, now this one is not giving us the velocity function. Now we have the position function. So let's keep that in mind. Well, if we need to figure out the intervals when the acceleration of the particle is negative, well then we must we're going to generate the acceleration function and do a time number line for the accelerations and find where they're negative. To do that, we must start with the first derivative, which is the velocity function, and that is negative 4t cubed plus 12t. Now to take the second derivative, which is the acceleration function, that is negative 12t squared plus 12. We want to know when the acceleration is negative. So things change from positive to negative when they are 0. So the next thing we're going to do here is we're going to set this equal to 0 and solve for t. I'm going to take out a common factor, which is, I can take that negative 12 out, which leaves me with t squared minus 1. Let's divide that negative 12 out, and then that's still 0. So we have this. We have 0 equals, now that's a difference of two perfect squares. We have t plus 1, t minus 1. Now you're going to get t equals negative 1 and also t equals positive 1. Remember, we're not dealing with negative time, so we have positive 1. Any event's going to start at 0 and move forward. So we take ourselves a number line, and that number line is the acceleration number line. So we plug them into the acceleration function to get the acceleration values. We know that at 1 it's a 0. Let's test on either side. Let's use well, how about 0.5, right? Because you got a 0. Let's not make that mistake again. Got to start at 0. And then how about we do over here 2? The acceleration function, let's just copy it down where we're working here, which was, that was negative 12t squared plus 12. And let's do this. Let's do a, we're going to evaluate 0.5, and a, we need to evaluate 2. When you plug in 0.5, this overall value is going to be a positive value. Go ahead and plug it into your calculator. And when you plug in a 2 there, well, that's going to make the negative term bigger, so it's going to be a new negative number. And what are we looking for again? Well, we're looking for where the acceleration is negative. So if it's negative in this interval right here, it looks like that interval is 1 to infinity. And that is your correct answer. In this example, we have ourselves a trig function, and it is given the position is 2 plus sine of pi times t. Part A is asking us to find the velocity and acceleration function, so why don't we go ahead and do that. Part A, velocity first. That's the derivative of position. The 2 goes away. This becomes cosine of pi times t times the derivative of the angle value. Let's throw that in front, because now when we take the acceleration function, well, that pi is just a constant. It's a coefficient, so we leave it. And now this becomes negative sine pi over t times the derivative of the angle value again. When we clean it up, we get negative pi times pi, which is pi squared. And there's your acceleration. Now for part B is asking us to find the position, the velocity, speed, and acceleration when the particle's at 1 second. Well, that means t equals 1. And just as a general reminder, speed, we talked about in the last video, that is the absolute value of velocity. All right, so let's find the velocity and take the absolute value of it. For part B, I want to find x of 1. Well, you plug in a 1, you're going to get this. Sine, well, pi times 1 is just pi, right? If you plug in a 1 right there. Do you know the sine of pi? Okay, here's a unit circle, here's 0, here's pi over 2, here's pi, here's 3 pi over 2, and then you go back to 2 pi. Okay, so we have ourselves sine of pi. Well, don't forget the sine is the y value. So what do we have there? We have ourselves negative 1 comma 0, which means that is 0. And that equals 2. For v of 1, well, v of 1, here's our v of t. So we have, that's pi times cosine. When you plug in a 1 right there, you get pi times 1, which is pi. So now do you know what the cosine at pi is? Well, we just said the cosine, well, we said the sine was the y value. The cosine is the x value there, pi, which is negative 1. So what we have is pi. This thing equals negative 1. So we have negative pi. And now, since we know that the velocity is negative pi, here, let's just change the color. Let's do it in blue. So speed. Speed is the absolute value of velocity, so the absolute value of velocity at 1, well, that equals, well, it's right, this negative pi, which means you take the absolute value, you get pi, so the speed is pi. Oh, and I'm forgetting the units. So what do we have here? The x is in meters, that's just a metric, it's just a length. And then we have velocity, well, that's a rate of change, that's going to be meters per second. And speed is the same thing, that's going to be meters per second. Now for the acceleration. A of 1, well, here's our acceleration function right here. So what we get is a negative pi squared sine. When I plug in a 1 right there where the t is, you get pi times 1, which is just pi. We already figured out sine of pi over there. Sine of pi, don't forget, we said it was 0. So this is negative pi squared times 0. Anything times 0 is 0. There's your acceleration at time 1. And since that is a rate of change of a rate of change, it is meters per second, you write it as meters per second squared. Next, let's find when the particle is at rest. All right, there's the last two parts, C and D. So part C is asking when is it at rest, and it's at rest when the velocity equals 0. So when does the velocity equal 0? I should have put my pi in front there, pi cosine of pi t. I'm going to divide both sides by pi, which just really gets rid of it and makes our problem a little bit easier. And now here we have to figure out so here the angle value, which is pi t, equals the arc cosine of 0. Okay, I did the unit circle up here to figure out some values. I'm not sure. If you like the curves, then think about the curves. Okay, so you know the cosine curve. There's another way to figure it out. So when does the cosine values equal 0? Well, it equals 0 right there and right there. So what are those values? I should have made that different color than black. Well, that right there, this is 0. This is pi over 2. This is pi right here. This is 3 pi over 2. And then over here we have 2 pi. So what we're looking for are those two values. And you'd get the exact same values if you use the unit circle here. So let's move on. Now at this point we have pi times t. Well, we just said that this thing can either equal pi over 2, or we have pi times t equals 3 pi over 2. So when you divide by pi, well, I'm sorry, I should do 1 divided by pi, right? That's multiplied by the reciprocal. And well, look what happens. They cancel out and we have time equals a half. Now over here, if we do the same thing, multiply by the reciprocal, you can divide also, but that leaves you with a complex fraction. And what is that? Those are going to cancel out, and you also know time is 1.5 or 3/2 seconds. Those are the times the particle is at rest. Now for part D over here, let's move it all up. D, I'm looking for moving to the left and the right. All right, so let's do D. We're doing the left and the right. So moving left and right, that's the velocity function. That's the movement of the x. And the values we got here for zeros were time equals a half and time equals 3/2. We start at 0, so we could take a test point of, say, 1/4. We can use a test point of 1, right? That's 2 over 2. And then how about 4 over 2? We could do a test point of 2. And we are going to plug it into the t value. We want to know the velocity. So the velocity function, let me just copy down here. V of t was pi times cosine of pi t. So we want to know when it is at 1/4. We get pi cosine, well, if t is 1/4, this is going to be pi over 4. And pi over 4 is radical 2 over 2. And don't forget to multiply that by the pi, so I'm just going to put it on this side. So we have radical 2 over 2 times pi. That is a positive number. So we get positive values. Now, when you plug in the 1, well, then what is v of 1? That's going to give you pi times cosine of pi times 1, which is just pi. The cosine of pi is negative 1. So that's going to give us a negative pi. And negative is negative. And if you plug in a 2, v of 2, you're going to get pi times the cosine of pi times 2, which is 2 pi. And 2 pi, well, that is 1, and I'm just, at some point you do need to know these values, and all I'm using is either these types of graphs or the unit circle I did above to memorize these values. And we've discussed them many, many times. Cosine, that is positive. All right, so we want to know when is it moving to the left. Well, it's moving to the left when the velocity is negative. That would be in between 1/2 and 3/2. And it is moving to the right when the velocity is positive, and that is from 0 to 1/2. And I forgot to give ourselves the ending point, which was 2 pi. That was a closed interval. So if you're saying that doesn't make sense, well, really all that is 2 times 3.14. So it's really like 6.28 seconds or so, okay, at the end. So that means we are going from 3/2 to 2 pi. Time to discuss speed and speed increasing and decreasing. We mentioned this in day 1. Speeding up is when they are these two functions have the same sign, and when velocity, acceleration have different signs, it is slowing down. Let's take a look at this problem. Particle moves along the x-axis. Here's our interval. We have the x of t graph. We have the position graph. Inflection points, 2 of them. Find all intervals of time when speed of the particle is decreasing. Speed of the particle is decreasing. Well, over there, that's slowing down. We are looking for opposite signs. Opposite signs for the v of t function and the a of t function. Well, from this graph, let's see where we're at. Regarding velocity, well, velocity are the slopes of the tangent lines, and since they're all negative over here, we have, I'm just going to write v. V is negative. And let's see over here, up to this point 8, in this interval, we have v is positive. Down here, 12 on this interval, we have v's are negative, and then over here, on this interval to 18, we have v's that are positive again, going uphill. I will do the other ones in green. A of t. A of t, well, here's the point of inflection. It's curving upward, so that is where, in this interval, that's where a of t, I'm just going to write A is positive. And then from this one to this one, which is that one, this interval, A is negative. And then from that point of inflection going up to this point, this is where A is positive. Now let's consider where we have to figure out where the V's, we're going to draw a V number line and a A number line. But first let's identify where the V zeros are, because 0 is where things change from plus to minus. And those little dots were on 12, and it was on 8, and it was on, I believe it was on 5 right there. Now we take those values and we're going to add them to our velocity number line. And we are starting at 0. Let's make this bigger so it's easier to see. 18. And from that interval, we said we had a 0 at 5, 1 at 8, and then 1 over here at 12. See, 12 is right there. Now from our graph, you can remember here we have the velocity was going downhill. It was negative before 5, and it was positive after 5, which means we have negative then positive. Then after 8, well, it's positive on this side of 8, and then it's negative on this side of 8. And then after 12, well, after 12, then the velocities are positive. They're going uphill. Next, let's do an acceleration graph. That also starts at 0, and it also goes out to 18. Now for the acceleration is the curvature. So where were those zeros? Well, the zeros for the acceleration are the points of inflection there. So it's curving. We had 1 at 6, and then we had 1 at 10, and that was it, 1 at 6 and 10. So now what we do is we put those on our number line. We put 6 and 10. And let's see what happens there. So before 6, it was curving upward. Right, I had that right there. And then it was negative, we had that right there, and then a positive after that, right? So watch what happens here. We're going to have a break here at 5, and now remember, that's blue, so this is still positive here, right? But then we change here, and at 6, so now to here, notice here, this in yellow, I got to change the yellow. This is still positive, this is in a positive region here. So what happens is this little section between 5 and 6 have the same signs, and we don't want that. But in this interval, we do want this, okay? So those are the opposite signs. So in between 0 and 5, that is, what are we looking for? We're looking for slowing down, speed decreasing. The next thing we have to look at here is, let me change that back to white. So now here's 8. Here's another breakpoint. Now, on this side of 8, you see that this is positive, right? Now, down here in blue, this is negative. So over here, it's still negative because it stayed negative up until 10. So we want this interval right here. We also want between 6 and 8. Now, like I just said over here, at 10, that's another breakpoint, and since this is negative over here and negative over here up until 12, right? These were negative and then these were positive. Well, if I draw that white line right here, this interval right here have the same sign in between 8 and 10. That's a negative, negative. I'm sorry, yeah, negative, negative. We don't want those. Those are the same signs. But then here, I just got done saying that 12, well, 12 is another breakpoint here. Now notice here, between 10 and 18, this is all positive region, right? So when I draw this little region, well, in between 10 and 12, we have opposite signs. So in between, we want in between 10 and 12, they have opposite signs. And then last but not least, in between 12 and 18, they have the same sign. We don't want that. So what are we looking for? We are looking for 0, 5, 6, 8, and 10, 12. These are the 3 regions where the speed of the particle is decreasing. For our next example, let's clear that out and clear this out. Wait. Okay. Here we go. All right, so for this one, it is looking for decreasing again. Now, I wanted to pick one that said increasing, but it really makes no difference. Just we're looking for opposite signs versus the same signs. I like this one, though, because it gives you the velocity graph, not the position graph. So let's look at it from this perspective. From here, we have the velocity values. Well, this is your positive interval, so it looks like it's positive. So we have velocity positive in between 2 and 7. And quite honestly, that's all we have, because down here in blue, we have negative. And it looks like it's negative between 0 and 2. And then even though this touches at 0, it's still from 7 down to 18. It's all in the negative region. So we have velocity negative. Now before I get involved with the acceleration on the graph here, let's draw ourselves a blue velocity number line. Let's start doing it the right way, starting at 0, and this is the right way we stopped at 18. So let's see what we have here. We said that we were negative up until 2, so this region was negative, and then that was 2, and then we said it was positive up until 7. And then we said from 7 all the way to 18, it was negative. Okay, that whole region was negative. Let's go back to the graph and talk about acceleration. Now, since this is velocity, let's do this in, hang on, let me find green. If this is velocity, then the derivative or the slope values, all right, the slope values is the derivative. So that's the acceleration values, and that's what we want. So here we have positive slope values. That's a 0 right there. So going from 0 to 5, our acceleration is uphill. It's positive. Then if you notice here, going from 5 all the way down, that's a 0 right there, up to 10. Okay, so that's a 5 to 10. We have acceleration is going downhill. It's negative. Then if you notice right here, these are all uphill. There's a 0 right here at 15. And so from 10 to 15, we have uphill slopes, positive, sorry. And then going from, we stop at 18. So that's where we have acceleration, negative. Let's keep that in green and draw the acceleration right below it in green. Okay, so the acceleration starting at 0, going out to 18, we said acceleration was positive up to 5, right? And then we said it was another 0 at 10. But then it also changed at 15 again. And let's see what the changes were. We said it was positive here. And then going from 5 to 10, it was negative. And then we said it was positive from 10 up to 15. And then it went downhill. Slopes were negative. Now let's see what we have here. In blue, if that is negative, this is still negative here. That was all negative, we said. And so is this. And here's where it was positive, and here's where it's negative. So we have positive in this region. Remember, in green, this is still positive. So let's see. This is this. Do it in white. These are different signs going from 0 to 2. And then these are the same signs right here. And over here, these are opposite signs again. That's going from 5 to 7. And our last interval where they're different is going from 10 to 15, because after that, they're the same sign. We don't want that. Here's our answer, these 3 intervals. Here we have a particle that's moving along the x-axis. Time is greater than or equal to 0, and they are giving us the velocity function. We want to determine all intervals where the speed of the particle is increasing. Well, the speed of the particle is increasing when we have same signs for both the velocity and the acceleration functions. So we're going to set these equal to 0. I'm going to start by setting the velocity equal to 0. And once you know we're at 0, then we can test points on either side to see if it's positive or negative. Then we'll do the same thing for the acceleration. I'm going to take out a common factor. We have t squared minus 4t. What is that, 3? So it's 12. I'm going to divide the 3 out. I think you've seen that before, so let's just continue. Negative 12. So I believe we need a negative 6 and a positive 2. All right, so this one is going to give you t equals 6, and it's going to give you t equals negative 2. We don't have negative 2 is not in our interval, so we have time equals 6. I'm going to do our number lines in the black region over here, so let me do it in white here. Let's start with the velocity. So for the velocity function starting at 0, and then down here we'll do the acceleration. All right, velocity, we have a point right here at 6. Let's just say 6 is right there. And, well, if we want to test points right now, we could do this. How about we pick, how about we do 1 and 7? When you plug those test points into the velocity function there, you have a 1 and you have a 7. Okay, so all I'm doing is plugging it into this function right here, 3t squared minus 12t minus 36. The 1, I have it on my calculator here, gives us a negative 45, and the 7, it gives us a positive 27. But, you know, what we're more interested in is what type of values do we get. In this region, we get positive values, and in this I'm sorry, I did that backwards. In this region, we get the negative values, and over here is where we got the positive values. All right, great. Now let's go to the acceleration function. If your v of t was 3t squared minus 12t minus 36, well then your acceleration function, which is the derivative of that, becomes 6t minus 12. When you set that equal to 0, let's see what we get. 12, move it over. Okay, you're going to divide by, that's going to be t equals 2. All right, so now what we have is this. I'm going to put a t equals 2 right here, and that is, now remember over here, we had negative here, which means it's still negative in that region, but we have to break it up because now we have 2 different regions here. And so down here now we'll do, I'm meant to do that green, so we're going to do the acceleration in green, so we're going to take a test point on either side of 2, so we're going to plug, how about a 1 right here, because don't forget that's 0, and how about we do a 3 over here. And again, that's going to satisfy anything over here. If you want to take another test point over here, say 7 or something, you can, but you're going to generate the exact same sign. Let's see what happens when you take this 1 and you plug it into the acceleration function. So that would be this. It would be, I plug that 1 into this function, and if you put a 1 there, you're going to get 6 minus 12, and 6 minus 12, well, that is a negative value. So you're going to get negative in this region. And what happens when you take this 3 over here? If I take that 3 and I plug it in here, well, that's going to be a 3 right there. That's going to be 6 times 3. That's 18. Guess what? That's when you start getting positive numbers. So over here, you're going to have positive numbers throughout, right? And let's see what we have. So we're looking for, when is it increasing? Well, increasing is the same sign, and we have negative and negative here. Those are the same sign. Here between 2 and 6, we have negative and positive. That's decreasing. Speed is decreasing. And here we have positive values. Again, for both of them, the speed is increasing. So the regions we're looking for, the intervals, I'm sorry, would be 0 to 2. And we also have, what would that, 6, right? So 6 to infinity. That would be the 2 intervals. Now we're given a rational function, and we're asked to figure out when the object is speeding up given the position function right here. Speeding up is when your velocity function and your acceleration functions both have the same sign. That's what we're looking for. So we're going to get the velocity and acceleration functions, draw our 2 number lines, and see what intervals have the same sign. Let's start by taking the derivative of this, which is the velocity function. And this is going to become 2. I'm doing the quotient rule. And it's all over the denominator squared. Let's clean this up. We have, that's going to be a 2t squared plus 2 minus 4t squared. That's all over t squared plus 1 squared. And now let's clean this up, and we have ourselves, what is that? That's going to be 2 minus 2t squared all over this. Okay, that right there is our velocity function. We're also going to need our acceleration function, so I will do the acceleration function next. We are going to take the derivative of velocity. So I'm going to do the quotient rule again. I'll take the derivative of the first, which becomes negative 4t, leave the base, or I'm sorry, the denominator, minus, I'm going to leave this, and now we take the derivative of the bottom, which is the chain rule. I put 2 in front, leave the base, reduce the exponent by 1, and don't forget to multiply by the derivative of the base, which is 2t. This is all over the denominator, which is this, squared. Let's clean this up. So I have a negative 4t. Remember, you can't distribute that into a squared factor there, so don't. But what can we do here? So I have this is a 2t times a 2, that's 4t. 4t times a negative, that's negative 4t. And then I'm going to leave this here, and I'm going to leave this here. I'm going to show you something. And then all of this, well, don't forget you multiply those exponents, that becomes t squared plus 1 raised to the 4th. Now, before we multiply all this and give ourselves it's a mess. If you notice something here, your life becomes a lot easier. This term and this term and this term, they all have a common factor. They have a t squared plus 1. So what I can do is this. I can say, well, they're all the same factor, so let me cancel one of them out here, one of them out here. Well, if I cancel 1 out here, I'm going to be left with 3. And I'm going to cancel 1 out here, which is going to leave me with 1. And what that's going to give us is this, negative 4t. This is just t squared plus 1 by itself to the first power. Here's my negative 4t, and I only have this. And it's all over t squared plus 1 cubed. I could go ahead and take out a negative 4t, but I'm not going to. I'm just going to clean this up so we can move on with life. That's cubed minus 4t, and then this is going to be, that's negative 8t, and then this one is positive 8t cubed. Okay, and do anything else? Yeah, we got some common factors here. So this is a cube, and this is a cube. That's going to give you 4t cubed. Sorry, that's a cube. And then this is negative 12t. And yeah, we could even take out a common factor there, but I'm not going to. Let's just move on. There is our acceleration function. Now to find out when the acceleration and the velocity functions have the same sign, to figure out when it's speeding up, we do this. Here's our velocity line and our acceleration line. And they both begin at 0. And let's see. We need to find the critical points for velocity and acceleration. So right here, this is velocity over here, right? So, well, what would make this undefined, right? We have a rational function. So what would make t squared plus 1 squared equal 0? That would be an undefined, that would be a point of non-differentiability. We have to consider it. Let's take the square root and square root. That's going to leave you with t squared plus 1 equals 0. And then you get t squared equals negative 1. And as soon as you do this, you might recognize that that right there is an imaginary number. We're in Calculus 1, and we only deal with reals. All right? So this is non-real. We don't consider it. All right, well, we still have to figure out what makes this thing over here equal 0. That's another critical point. What I like to do is cross multiply. And what you're going to get is 0 equals this. I'm going to do this. I'm going to divide both sides by 2. And I'm going to get, you do this, and you get t equals plus or minus 1, but you can't do time equals negative 1, so we have time 1. Now for this denominator, you got to be mindful, because what you want to know is what's going to make t squared plus 1 cubed equal 0. Well, if you think the cubed, maybe you can have the negative 1 under a cube. Well, you're right, but that's not what happens, because now all you're going to do is take the cubed root and the cubed root, and then you're going to have t squared And you see how you're left with the same thing. You're going to get yourself an imaginary number. So let's spend time finding the other value when acceleration equals 0. I'm going to cross multiply. And you're going to get 0 equals 4. Here, let me do it over here. 0 equals 4t cubed minus 12t. I'm going to take out a common factor of a 4t, which leaves me with t squared minus 3. You set this one equal to 0, and you get t equals 0. You set this one equal to 0. Whoops. And you're going to get t equals plus or minus radical 3, but we can't have negative time, so we have time equals radical 3. We put those on the number line. Here's 0, and here is radical 3. Radical 3 is approximately 1.732-ish, just to give you a frame of reference. Now for test points. The velocity function we said was 2 minus 2t squared over this. And we want to test what's the velocity. Let's take a test point. If that's 0, how about we do a half? And we can do 2, right? And let's see, so 1/2 and v of 2. In the interest of time, because these are getting very long, these videos, you can plug in these values. This is what happens. At time 1/2, the velocity is a positive 0.96-ish, which means it's positive. And then when you plug in a 2, you get negative 0.24-ish, which is negative. And that's the difference there. Now for the acceleration, I'll do in red. Here's the acceleration function. I'll copy it down again. It was 4t cubed minus 12t all over this. We're going to do the same thing. We need some test points. So let's go over here. And we had 0, which is at that endpoint, and we have radical 3 over here. So, well, radical 3, so why don't we do 1, because that's less than 1.7, and we could do 2. That's right, bigger than 1.7. So if you plug in so we want to know a of 1 as our test point and a of 2 as a test point. Here's the values we get. Plug in 1 into this function, and you're going to get a negative 1. Plug in a 2 into this function, and I got a positive 0.064, which means we have negative values on this side, right? Negative here and positive over here. But remember, here are our intervals right here, this breakout. So if you have negative across here, there's negative acceleration here and negative acceleration here, and there's positive acceleration here. Since over here, negative velocity, there's negative in this interval and there's negative in this interval. So now let's see what we have in, let me find here, this orange. So in this interval right here, we have velocity and acceleration have different signs. In this last one over here as well, they both have different signs. It looks like the only place they have the same signs is in between 1 and radical 3. So that's where it's speeding up. Final topic to discuss in this video is total distance of a graph. Now we talked displacement. Displacement is the change in position over a time interval. I'm just going to do quickly one displacement to remind you. So if it's the x of b over x of a, well, let's see what that is. We have x of b minus x of a, which means we have the end point over here, so it's x of 18 minus x of 0 is where we started, and that was a negative 6 minus a 5. We have a displacement of negative 11 units. That just means we're moving, it's negative 11 units to the left of where we started. Okay, that's the displacement. Now let's move on to total distance. Total distance is how much ground do we cover throughout this interval, right? So let's track these times. Now remember what we said in the first video. Here we're walking towards the left. Now even though we're walking in the negative direction, I'm not going to treat that as negative distance because we want to add it all up. We want the absolute value. So we have to figure out, where does our graph turn around? They change direction or turn around at relative mins and maxes. And right here is a dot. We had a relative min at 2. Here's a dot. We have a relative min at 7. And even though that's a dot, that's a 0 slope. It's not a relative min or max because you just keep decreasing. All right, well, that means we're changing direction at 2. So from 0 to 2, we're doing some sort of distance. And then we change direction up until 7, right? So in between here, between 2 and 7, we have some sort of distance we have to add. And then we just keep going downhill. So from here, we go all the way down towards negative 6, and we stop there at time 18. So our last interval is going from 7, and we just keep walking in the same direction down to 18. What is our values here? Well, we are going, let's see, so this is going to be 5 units, and then we have 3 more units, right? So that's going to be a total value of 8. Going from 2 to 7, well, from 2 to 7, we have to go back 3 to the 0, and then up 3 after the 0. So 3 and 3 is another 6 units total. And then we're at position 3 here, but then we walk all the way down to position -6. So what is that? Well, that's 3 units this way, and then another 6 units that way. That's 9. You add that up, and we have ourselves a total distance of 23 units, going from time 0 to 18. Let's see how to go about one when we're not given a graph. Here's a cubic function. I'm just copying it down from the problem up there. 24 minus 46. All right, so that right there is the position function, and we see that we want to know the total distance going between time equals 0 and time equals 3. All right, well, we still want to go, what did we do before? We found our mins and maxes. So the mins and maxes would be where the velocity equals 0. Remember, you take the first derivative and set it equal to 0? Let's do that. We're going to get 3t squared plus 6t minus 24. And then we set this equal to 0. I notice that these are all divisible by 3, so why don't we take out a common factor and make our problem easier? Plus 2t minus, that's a 3, so that's 8. I'm going to divide both sides by 3, gets that rid of there, and then we can factor this. Let's see what we get. -8, so we want ourselves. Okay, is that right? That is right. All right, and then what we do is, you set both of these equal to 0. We're going to get a -4, which we are going to ignore, and we get a time equals 2, which we are going to use. So that means that we are going in one direction until we hit our little t equals 2 here, and then we change direction and we go somewhere else. So because we're going from... So we need to figure out if we're starting at 0 somewhere, and then we're going out to time 3, we have to figure out what distance we're going between 0 and 2, and then what distance between 2 and 3. This right here has the values. Just to save a time, you can plug it into your calculator to check. But if at time 0 here, when you plug in a 0 into the position function, you're going to get a position, and you actually are pretty low. You're down at -46. And then what happens is at 2, what happens, you're at -74. So if you're going from -46 down to -74, well, that's a total distance of 28 units. Then right here at 2, you switch, and going from 2 to 3, well, at 2, you're at -74, and then you go to 3, your new position at time 3 is -64, which is a distance of 10. Again, we want the absolute value, so we can add everything up. You take those two distances, we have a total distance of 38 units.